The Earth has one natural satellite flung into its place by nature billions of years ago, and still moving serenely across the skies, lending beauty and mystery to many of our nights. The invasion of space near the Earth by man-made moons has diverted man's attention, perhaps, from the Earth's natural satellite, the moon, its nearest permanent neighbor in space. And obviously the first target for the exploration of space by man. Until a very short while ago, 350 years ago, the moon was regarded with some awe and superstition as a strange phosphorescent object in the sky. The first man ever to look at the moon, or indeed at anything else, through a telescope dispelled that illusion. That was Galileo. And in 1608, he saw the moon as you're seeing it now, through a telescope. Of course, not as clearly as that, for his telescope wasn't as good as the one that we're looking through now. The moon was seen by Galileo and by the other early astronomers to have strange dark areas upon it. And they assumed, by a sort of an analogy with the Earth, that these areas were covered with water and were like our oceans and seas and so on. We know now, however, that these dark areas are relatively smooth places. Here is an artist's idea, perhaps, of the surface of the moon. And we can see some of these smooth regions. We can see the mountains on the moon, perhaps not as weathered as these look, but a little more rugged. We can see the dusty surface of the moon, and we believe there is great dust there. Here is one of those strange craters that we are going to talk about, and the little isolated peaks that seem to rise above the surface of the moon. It's a very strange place. These dark areas on the moon were given by the early astronomers the names of oceans and seas. And we still call them that, although we know that there is no water there, that they are perfectly dry. Here is the moon's only ocean, on the left-hand side of the moon as we see it. And we must wait at least until full moon until we can see that. This is the ocean of storms. It is bordered in this direction by the Sea of Showers, a smaller dark area. And on this side, by the Sea of Clouds. The Bay of Rainbows juts out of that Sea of Clouds. There are 5 other smaller dark regions or seas on the right-hand side of the moon. We can see them here. The Sea of Serenity, the Sea of Tranquility, the Sea of Fertility, and the Nectar Sea, all very happily named. There is one exception, however, and that is the Sea of Crises. And above the moon, the upper side of it, is the moon's Arctic Ocean, if you will, the Sea of Cold. Now we can see a close-up of the Sea of Tranquility and the Sea of Serenity. That dark area, marked with smaller markings and craters, and with that curved mountain range just below it. For there are considerable mountains on the moon. Indeed, the mountains on the moon are relatively much higher above the surface of the moon than mountains on the Earth. Down here are the Leibniz Mountains, some of whose peaks rise above 30,000 feet from the surface of the moon, whereas the highest peak on the Earth is Mount Everest, about 29,000 feet. Here are 2 peaks which seem to spring abruptly from the general level of the plain, Pico and Piton, rising to heights of about 15,000 feet. And here is a close-up of Pico and Piton. See them casting their sharp shadows over the plane of the moon. And just to the right of them is the great range of mountains known as the Alps, for many of the mountain ranges on the moon have the same names as mountain ranges on the Earth. And you can see cutting through the Alps there like a chasm, the great Alpine Valley. Here are the Alps in relation to the rest of the moon. And here are the Caucasus Mountains. And here are the Apennines. And across here are the Carpathians. One of the strangest formations on the moon are these round depressions, which we call craters. Here is a typical crater. Now, craters is not perhaps the best name for these things. They are not craters as we picture them on Earth, rather steep cones with a small depression in the top. It might be better to call them walled plains, for they are big. The biggest walled plain on the moon is this one. Its name is Clavius, and it is 156 miles in diameter. There are several smaller plains, or craters indeed, inside of the moon. Two of the most prominent craters on the moon are Tycho here, and further up, Copernicus. They are each about the same size, about 54 miles in diameter. And here we can see a close-up of Tycho, of Copernicus rather. The mountains which ring this crater are about 8,000 feet above the level of the plane of the moon, and the center of the crater is depressed below that level. And in the center of this crater, as in the center of many of the large craters on the moon, there are central peaks, in this case a cluster of 7. And you can also see the system of rays, those light markings, which radiate out from the center of Copernicus, overlying the darker areas. These are strange and mysterious. They do not have any height, for they cast no shadows, and they look like lighter material cast out, perhaps, of that crater. There are about 30,000 of these craters on the side of the moon we can see, and most of them have been measured and named. Now, they are named, in most cases, for individuals who have made notable contributions to astronomy. In order to qualify for a crater on the moon, you must satisfy 2 requirements. You must be a first-rate astronomer, and you must be dead. The causes of these craters, we still don't know. There are many schools. Some say that they are volcanic, although their broad, rather shallow outline makes that a little difficult to believe. Others say that these are the scars left by the impact of tremendous meteors, which smashed into the moon ages ago in the great turmoil that attended the birth of the solar system. Still another theory is that there was a sort of a sluggish volcanic action which lifted the crust of the moon up without breaking through it. And then as that action subsided, the material below, the pushing material, sank. And eventually the roof fell in and left these great hollows. There are still, well, some shapes that we believe to be domes on the surface of the moon. The apparent change in the shape and appearance of the moon, its phasing, which was such a mystery to people thousands of years ago, is due to 2 factors. One is the moon's slow rotation. It's turning upon its own axis, and the other is its revolution, its passage about the Earth. Now, we know this, that one side of the moon is always fully lighted by the Earth. In this little model, here is, of course, the lighted side, and here is the dark side. Now, the lighted side of the moon is that side which is looking toward the sun, for there is where the moon gets its light. It has no light of its own. At this time is the time of new moon, when the moon is generally between the Earth and the sun. And we can see that the side of the moon turned toward the sun gets all the light. The dark side of the moon is turned toward the Earth. At the technical, astronomical new moon, we cannot see anything. A few days later, however, when the moon has moved eastward around the Earth, we can begin to see just the edge of that lighted side. In a little while longer, we can see half of the lighted side. About 2 weeks after new, when the moon has gotten around to the side of the Earth opposite the sun, we can see the complete lighted side, and that is full moon. Of course, we're looking at this thing from an imaginary viewpoint in space, but this shows you what the Earth sees. After full moon, the moon keeps right on going, of course, and we begin to see a lessening of that lighted side. Then we see another half, and finally the cycle is complete when we get around to where the full moon, where the new moon started. Now, here's a diagram that explains that perhaps a little more clearly. Here is the direction in which the sun's rays are coming. This inner ring shows the moon as it is lighted by the sun. Always, you see, a complete half of the moon is lighted. The outer ring shows the moon as we see it from the Earth as it goes around. Here is the Earth, here is the moon as it is really lighted, and here's what we see. We see everything inside of this line. Here we see nothing because there is no light coming to us from the moon. The lighted side is turned away. This is new moon. Here is a very early crescent moon. You see, we are just seeing the edge of the lighted side. Here we are seeing half of the lighted half. Now, half of a half is a quarter, and this is called first quarter moon. Here we see a little bit more than half of the lighted half. This is the shape which we call the gibbous moon. It comes from an Italian word, gibboso, meaning hunchbacked, and this is the hunchbacked moon. Here is the full moon. Opposite the sun, the fully lighted side turned toward the Earth, and we see the full moon. Then another gibbous moon. Then the other half of the lighted half that we saw here last quarter, the other crescent of the moon, and finally completing the cycle around to new moon again. Now we have some excellent pictures of the moon, which are over here, which were taken at one of the great observatories, which show us these phases. Here is what we call the new moon, the early crescent. It shows us just the edge of the lighted side of the moon. And notice that the points of the crescent are turned away from the sun, and of course the curve of the crescent is in the direction of the sun. Here a few days later is the moon almost at its first quarter phase. Then we have the gibbous moon, more than first quarter but less than full. Here is the full moon. And it's at this time, incidentally, that the markings on the moon may seem to people with lively imaginations to resemble the full face of a man. Here is the man in the moon. Then we have another gibbous moon, a hunchbacked moon. Then the diminishing moon. Here is last quarter. The crescent gets a little bit smaller, and finally we have another crescent. But this crescent, you have to get up very early in the morning to see. This is the last crescent. Now, this crescent business may puzzle us. Crescent means growing, but in this case, we have taken the shape for the action. This is called the crescent before new, or the waning crescent, the decreasing crescent. The other crescent is the crescent after new, the waxing crescent, or the increasing crescent. The moon is not very big. It has a diameter of 2,100 miles, which is a little more than a quarter of the diameter of the Earth. Actually, however, the moon's size in relation to the size of the Earth makes it the biggest of the satellites in that relation in the solar system. Now, I don't mean that there are not satellites which are bigger than the moon. There are. But in each case, these satellites are smaller in relation to their mother planet, if you will, than the moon is to the Earth. You might almost call the Earth-Moon a dual planet system. The density of the moon is much less than that of the Earth, about 3 1/3 times that of water against the Earth's 5 1/2 times. And that makes us believe that there is no solid metallic crust to the moon as there is to the Earth. The moon is made up of material very much like that on the surface of the Earth. And that has given rise to one very interesting theory, is the origin of the moon. It is supposed that the moon was flung away from the Earth by the Earth's very rapid rotation in the early days, something like a piece of mud snapped away from the tire of a wheel. And some people have even gone so far as to say that the Pacific Ocean now fills the vast hollow which once contained the material of the moon. However, this is simply a theory and mustn't be accepted yet as fact. The moon moves around the Earth at a rate of 0.6 of a mile per second, or 2,160 miles an hour, and takes 29.5 days to make a complete circuit of the Earth, as we see it doing here, going once around. From new moon to new moon, from the one phase to the corresponding phase, takes 29.5 days. Now, there is another way of measuring the moon's revolution, and that is by the stars. Suppose we have a star here just lined up at this moment with the moon. Now, as the moon goes around the Earth also moves around the sun. And we shall see that that shortens up this time. Now watch what happens. We have lined up the moon and a star, any star. So we move, and the moon goes around the Earth. But when the moon is again lined up with that star, it has not had time to complete its revolution about the Earth. Now, the first passage of the moon around the Earth was called its synodical revolution. That is a Greek word and means traveling in the same road because the moon and the Earth are moving around together. This passage of the moon around the Earth is its sidereal revolution, or its revolution according to the stars. Sidereal comes from the Latin word sidus, which means a star. The moon moves about the Earth in an elliptical orbit, as do all of the planets about the sun and almost everything else that moves in space. And because of this, the moon is a great deal nearer to the Earth at one point in its orbit than it is at another. At this nearest point is called perigee. Now, you remember our old friends perihelion and aphelion. Well, this is related to it. It comes from the Greek peri, meaning near, and G, meaning Earth. We use that same root for Earth in geography. The distance of the moon at perigee is 222,000 miles from the Earth. The distance when the moon is at the opposite point of its orbit, at apogee, apo meaning far, and again G, is 253,000 miles. The mean distance of the moon from the Earth, the halfway point between these two, is 239,000 miles. And that is the distance that is usually used in speaking of the moon. Now, something very strange happens to the moon as it goes around the Earth. The moon is near the Earth. The Earth's attraction, gravitational attraction on it, is very strong, and it has slowed down the moon's ability to spin upon its axis until the moon makes just one turn on its axis as it makes one revolution about the Earth. Now, here we have colored this so you can see which side is which. This is the side facing the Earth now, and this is the side away from the Earth. Now, as the moon revolves about the Earth, it turns just once, and the result of that turning is that the moon always keeps the same side of itself turned toward the Earth all the way around, and you can see that this side has gone around the moon. In other words, the moon has made a rotation, but we have never seen but one side of the moon. Now, an eclipse of the sun is one of the most vivid, most awe-inspiring sights that man can see. And, of course, it is the moon that is responsible for an eclipse. The success of the moon's work in this respect is due purely to an astronomical coincidence. The reason, that is, that the moon and the sun fit so neatly together at such times. Actually, of course, the sun is 400 times as big as the moon, but it is also 400 times as far away. So perspective makes them appear to be the same size. Or put it another way, the sun and the moon are both 110 times their own diameters away from your eye. And any round or spherical object, a dime or a soup plate or a basketball, if it is 110 times from its own diameter from your eye, will look to you just as big as the sun or the full moon. Try it with a dime sometime. You'll have to get a friend you can trust to hold the dime, because 110 times the diameter of a dime is about 70 inches, and your arm isn't long enough. And take a bit of advice. Try it with the full moon and not with the sun. It's more comfortable that way. Now, an eclipse of the sun is caused by the passage of the moon directly between the Earth and the sun. And it must be new moon, because that is the time when the moon is between the Earth and the sun. At such times, the moon's cone of shadow, tapering down to a point, strikes the Earth. And at the Earth's distance from the moon, 239 100,000 miles on the average, there isn't very much left of that shadow. It makes a little dark spot on the Earth, about 160 miles in diameter. And because of the motion of the Earth, both rotation and revolution and the motion of the moon around the Earth, the shadow travels very rapidly across the face of the Earth. Here is a diagram of the shadow path of the eclipse of June 20th, 1955. That total eclipse began at sunrise in the Indian Ocean just east of the coast of Africa. It traveled across the island of Ceylon, across the Malay Peninsula, across the Philippines, and lost itself at sunset in the middle of the Pacific. Now, the length of time it took the shadow to go from Africa to the middle of the Pacific is about 3.5 hours. So you see, the shadow doesn't linger very long in any one place. The longest possible time that the moon will completely cover the sun during an eclipse is a few seconds more than 7 minutes, and several special circumstances have to be present to make that possible. The moon has to be at perigee, fairly near the Earth, so it looks big. The path of the shadow has to cross the equator, and the observer has to be on the equator to see the full 7 minutes of such a lunar eclipse. This one in Ceylon was one of those long eclipses, and people came from miles around, astronomers, with their complicated instruments to see it. And what happened? It was so cloudy that very little was gained from the observation of that eclipse. That fate seems to pursue such astronomical events. Now, there are times when the moon does not completely cover the sun during an eclipse. That would have to be when the moon was at apogee, rather far from the Earth, so that perspective made it look smaller. Then, if the observer stood in the shadow, he would see a thin edge of sun around the edge of the moon. This is called an annular eclipse, from the Latin word annulus, meaning a ring, because there is a ring of sun visible around the edge of the moon. Now, here is a film of an annular eclipse, which shows just that effect. There you see the sun and the moon beginning to cover it, beginning to come in. The eclipse always begins from the right, from the west. Generally, this is coming down from the upper right. See the moon creeping over? Now watch. In just a few seconds, the centers of the moon and the sun will coincide. And you'll see. That jerky movement, by the way, means that the man didn't have a machine-operated telescope. There it is. There's the annular eclipse. See that ring around? That is of no scientific value, frankly, because that ring still makes so much light that the wonders that you can see at a total eclipse aren't available. Now, here is a total eclipse. The moon is near the Earth. The observer is in the center of the shadow, and he sees the sun completely covered by the moon, but he can also see one of the phenomena of the sun, the corona, which up till a few years ago could only be seen at the times of total eclipses of the sun. To see a partial eclipse, the observer would have to be out of the main shadow of the moon and in the partial shadow. Then the angle at which he looked at the moon and the sun would leave a bit of the sun still visible all the time. It would never be completely covered up. Now, we have some films of several eclipses, which have been put together to make a very interesting sequence. But before we go into that, here are some of the reasons, the additional factors that must be present during an eclipse. The orbit of the moon around the Earth does not lie in the same plane, doesn't coincide with the orbit of the Earth around the sun. If it did, we'd have an eclipse every month. As it is, the moon in many cases passes above or below the center line connecting the sun and the moon, and we don't have an eclipse. The moon, however, crosses the path of the Earth's orbit, the plane of it, twice each month. Once from above to below, and again from below to above. And when this crossing of this node, that's what these crossings are called, occurs at the time of the new moon, there will be an eclipse. Now, these circumstances don't get together very often. There can be no more than 5 total eclipses of the sun in any one year, and there are rarely that many. There may be as few as 2, and there are usually 3 or 4. Now, here is that film of the eclipse. This is the eclipse that we just saw on Ceylon. And you can see some of the elaborate and heavy equipment which had to be brought from miles around to see that eclipse. They set it up here, and they drill, and they practice, and they rehearse for weeks to get every bit out of the eclipse, to take full advantage of that 7 minutes. Now, this is an excellent picture, but unfortunately, the eclipse was marred, of course, by cloudiness, as I said. And here we can see those clouds. And the eclipse is almost at total. You can just see the edge of the sun before the moon slides in front of it. See how it's getting darker? And then the light of the sun is almost cut off. And you can begin to see some of these things which are visible around the edge of the sun. These are the great hydrogen prominences that show around there. You can just see them faintly through the murk, through the clouds that were overhead. This was a wonderful job of picture taking, even to get this much of it. And now, in a few seconds, you'll see them on the other side of the moon as the moon slides on across the surface of the sun. There they are. See them down below. There, now it comes out, and watch the light grow. See it spread out. Now, here is another eclipse when the clouds weren't in the way. Now, watch. This is the diamond ring. See that diamond ring? Now, that is the last vestige of moonlight shining through a great gorge or valley up on the moon. And what you're looking at now is the corona, the sun's outermost atmosphere. And this is the corona during a time of very small sunspot activity. It's characteristic then, close to the sun at the poles of rotation, above and below, spread rather wide at the equator. And watch for another diamond ring now coming in from the lower right as you look at this. There must be other mountain gorges down there, and you can see the light of the sun first appearing there. Here it comes. Watch now. The diamond ring will appear at the other side. There, see it? Now we'll see a speeded up motion picture of the moon moving away from in front of the sun. That is the story of the solar eclipse. Comes to the last contact when the moon vanishes from the sun. Now, there can also be eclipses of the moon, but these are caused not by the passage of the anything in front of the moon, but by the passage of the moon through the shadow of the Earth. The Earth has a cone of shadow 865,000 miles in length, and where the moon passes through at 239,000 miles, it takes about 4 minutes to go through. At that time, the moon doesn't disappear. It takes on a strange, weird, reddish color, which is caused by the action of the Earth's atmosphere on the sunlight shining on the other side of the Earth. The bending effect of the atmosphere fills that cone with this weird red light, which we see then.
Such are the varying aspects of the changing and changeless moon. It is obviously man's first goal in space, although why he should want to go there very badly is more than I can understand. Perhaps for the same reason that the great British mountain climber Mallory gave when asked why he wanted so badly to climb Mount Everest. Mallory said, "Because it is there."
This is NET, National Educational Television.